x values close, so that's kind of arbitrary, close to A. Okay? So it's only good for some little window around A, right? So let's construct the tangent line from what we have so far. The tangent line would be what? Y equals, what's the slope? It's going to be f prime at A, right? Yeah. Okay. So f prime at A, there's our slope of the tangent line, right? F prime A. And what's that? You multiply by x, and then what? Plus b. So we just need to find the y-intercept, right? It's all in the abstract right now. Find y-intercept. I'm going to get to a little formula. So we know x and y is a particular location. No, it's a comma f of a, right? X, y pair here is a comma f of a. So the notation gets a little burdensome, a lot of parentheses. So we'd have f of a equals f prime a times a plus b. This will allow us to find b for this particular tangent line, right? Remember that the derivative, the slope here is known, and the function at this value a is known. These are all known except for the b right now, and a given problem. So it looks like b equals what? I guess f of a minus a f prime a. All right, so our tangent line looks like y equals f prime at a times x plus the b plus f a minus a f prime a. There's our tangent line. Now we can group together these two pieces since they both have f prime a attached to them. To write it more concise, we'll factor that off. We'll write it as y equals f of a plus f prime at a x minus a. Everybody understand that little factoring at the end? No big deal?
Yeah, what you did?
So all I did was I moved the f of a right here. That's the function height there. And then I grouped these two together, and I took off the f prime a. So f prime a came out, and I was left with x minus the a. So that's a little factor there.
Love that.
Okay. So this is equation of tangent line. Equation of tangent line to f at a. So what we're going to do now is we're going to use this as an approximate to the function itself. So for values that are, say, close to a, somewhere in here, you can go out a little distance from a. We'll call it x, not x. And that would map up to this location here on the tangent line. That would be the value. So in other words, if you took this x, which is a little bit away from a, and you put it into here, right, put it in for x here, then the y that comes out of this expression is going to be that dot on the tangent line. Okay? And it's going to be close, it'll be an approximate to the actual dot on the curve, right? That value there is f of x itself, right? If that's x, you really want this, but you can't get it. For whatever reason, you can't get this through conventional means. You don't have the function itself, per se. But you can get something that's close to it. You only have this very small margin of error here, right? When that little bit of error, there's the error away from the actual value, okay? So now this works as long as you're close to A. You start moving too far away from A, start putting x values way out here, and then the tangent line, especially if this thing is, keeps on going in this particular manner, the tangent line value is going to be too far away to be considered a good approximation. So it's for values which are close, but we're leaving close kind of a nebulous concept at this point. Raj, you going to say something?
Yeah, you said if we put in A, we can find the approximation for the x group.
No, if I can put in x, I can put in some number which is around A.
Oh, okay, into that equation.
I can put it into this equation, which is this tangent line. It will give me that red dot on the tangent line, which is close to the blue dot on the curve, which is what I really want to find. Okay? This distance here, that distance there, is this difference x minus a, right? That distance is the difference between the value you're putting in to the tangent line, right? Expression here, and it's difference from a. It's just the distance between x and a. That's that. And this here, right, is what? Change in y on this curve. The change in y on that curve is going to be what? It's going to be equal to f prime at a times x minus a. Right? So that's why this thing makes some sense, right? You take the actual function value here, right? You know f of a already, so that's that height there, right? That height is already f of a. That's the first height there. And if you add to that, right? You take f of a, you add to that this change here, which is f prime at a times x minus a, right? It's the derivative here, right? It's that slope. It's this slope of this line times that distance which traveled gives you that change in y. You add those two things together, and you're going to get that dot right there, which is an approximate to the function value, not actually on the curve. So in the textbook, they're not going to use y for this though. They're going to write it like this. They're going to write t. I'm sorry, no. I think I used L. L for t. Sometimes they use L for linear. Sometimes they use t for tangent. They use L for linear. Okay. So here's our linear approximation. Linear approximation is L of x equals our formula down there. So instead of y, they use L of x. A plus f prime a x minus a. There's our formula. So now, in many of the problems, they give you the x and the a. They give you the x to put in and the a. In other problems, they don't. So you have to pick a good value for a, so which x is close to. And we'll do a couple. See if you guys get it. Now, in my picture, the approximation I've made here, the red dot, right? The red dot is our approximation. Right? And the blue dot is the actual. So there is some error. There's always going to be some error between them. So now is mine an underestimate or overestimate? Underestimate. It's under. And you should always expect it to be an under if the function has what concavity? Yeah. If the function is concave up, you should expect an underestimate. And if the function is concave down, you should expect an overestimate. Not only that, depending on, yeah, go ahead, Justin.
What did you add?
I was simply saying there's always going to be some error between our approximate value and the actual value, right? In the case where I've drawn a picture where the curve was concave up. So if the curve is concave up, then all the tangent lines lie underneath the curve. We said that last time when we were talking about concavity. They lie underneath. So since they lie underneath the curve, then when we take the approximation, it's always going to be an underestimate to the actual value.
Okay.
If the curve is concave down, it will be an overestimate to the actual value. Now, how bad is the overestimate or underestimate? They'll depend on the concavity of the curve. So the larger value the concavity has, that is the second derivative, the larger absolute value the second derivative has, the worse error you'll have.